All right, let's start working through this together. What would be our first step that we do? Josh?
You got to get to 100%. So add up all the percentages you have, and what's left over should be oxygen.
Great. So we know, I think from the previous wording of this question.
Caffeine.
Yes.
Oh, no?
There you go. Oh, no.
Previous wording.
The wording of the question, that this compound has what elements in it? Did I say that in the wording of the question?
Yes.
Carbon, hydrogen, nitrogen, and oxygen, right? And so what Josh pointed out is really important, that this doesn't add up to 100%. But we don't say how much oxygen there is, and we don't find that from elemental analysis. So what did you find for your percentage of oxygen?
16.8. 4.8, sorry.
So the percentage of O is, say again, 16.48%. That's what's missing to get to 100%. So we know that out of the total mass, of any total mass, 16%, 16.48% of that comes from oxygen atoms. Okay, great. What is the next step that we do? A lot of people might want to skip this step, but it's really important to me, conceptually, that I understand that you understand what you're doing. Jackson?
Okay, so if you have percentage of something, that's out of 100, right? So you can just convert the percentage into grams if you have 100 grams of the substance.
Okay, exactly. So I think a lot of people are like, oh, percentage, that's grams. No percentage is not grams. So you have to say, if I have 100 grams, then I have 16.48 grams of oxygen. Do you see the big distinction there? This is not grams, but if we have 100 grams, then that's how many grams of oxygen we have.
I thought we were basing it off 50 milligrams.
So does the percentage change if we have 50 milligrams or 100 grams?
No, the percentage doesn't change. I just found...
So totally fine. And I saw a number of people do this. So they said, okay, well, if we have 50 milligrams, then 16.48% of that is how many milligrams of oxygen we have. Is that an easier calculation, or is it easier to do it out of 100 milligrams or 100 grams?
I mean, yeah, it's easier. This took me way longer, but I thought I had to use the specific amount.
Yeah, so the nice thing about percentages is that we don't have to use any specific mass. And that's a way to save a lot of time. So a couple people I saw around the room were doing that. They were taking the 50 milligrams. What is 49.48% of 50 milligrams? You can kind of do it in your head, but it's better to do it in a calculator, but then you have all these extra calculations. So my suggestion is pick a mass that is divisible by 10, because these are percentages. Like Jackson said, they're divisible by 10 or 100 very easily. So you could do 100 milligrams, you could do 100 grams, you could do 10 grams, whatever it is. If you don't show me on the exam that this is assuming this many grams of it, and you just convert percentage to grams, that I'm not going to be happy.
Can we just put that like...
You just say assume 100 grams or assume 10 grams. And then all of your masses of each element will come from that calculation of, let's say we use 10 grams. Then we'd have 0.5190 grams of, what is that, hydrogen? Right? So you'd have to tell me that you're not just assuming percentage of grams. That's what I'm asking you to do. Okay? So if we do that, we can say, well, I know how many grams of each element we now have, now that we're starting from a specific mass. And once again, the mass doesn't matter as long as we use the same mass for each of the elements. What do we do next? Go ahead, Ruby. Okay, so if we know how many grams of each element we have, we can use the molar mass to find the number of moles of each of those elements. So I do typically use 100 grams. Granted, we should never use this to limit our sig figs, so we should have a lot of sig figs, a lot of digits there. And then for each of the elements, I found how many moles of each of those I had. Another common mistake that's made. That's about 1. That's fine. We'll just round that down. We'll round this down, we'll round that down, we'll round that down. Okay, we're good. No, don't do that. Don't ever round at this step. and actually store all these numbers in your calculator. If you still have trouble storing numbers in your calculator, please come stop by. I'll show you in 2 seconds how to do that. That way you store the full number without rounding. And that's especially useful in this case, because if we store all these numbers, then the next step we can just say divide by stored A. The number that's stored, and then we don't have to retype in the number. It becomes way easier. Okay, so now we have a whole bunch of numbers, and if we did 50 milligrams, then these are going to be totally different. They're not going to look like this. It doesn't matter. What do we do next? Now that we have the number of moles, Kayla?
Divide all of those by the smallest mole amount.
Why do we divide by the smallest mole amount?
So you don't have a fraction. Weird fraction.
Okay, there's a little qualification. So we don't have any numbers less than 1. That's really what it comes down to. We have fractions. Fractions are fine. But if we divided everything by 2.059, then our smallest one is going to be less than 1.
Can't have that.
We can, but then we have to multiply, and it just becomes easier to see our smallest number in the ratio to be 1.
Well, the way I like to see it is, can you have a half an atom?
Right, so we can't have any fractions, which I think was Kayla's initial point. But my point is that if we divide by the smallest number of moles, then everything is 1 or greater as far as numbers. So let's go ahead and divide everything by 1, 0.029. And now we get super close to 2, to 5, and to 4. When you're asking yourself, is this number close enough to round? This is the stage that we ask that question. We don't ever do it before this. And these numbers should be really close to a whole number, or what else do you find them close to?
Is it 0.5? In which case you would do 2 of those in that element?
So if we had gotten 4.499 as one of them, we're not going to round up or round down. We're going to say, well, like Jackson said, we can't have half an element in a molecule. So then the whole ratio has to be doubled to make sure this is a whole number. The other numbers we very typically find are, what does this tell us? What is this in fraction form? Third. We'll also frequently find, which is a fifth. And then the one other one that you might find is a quarter. So you need to be looking for the fractions within the decimals on the side. And that will tell you what ratio you need to look at to find your whole number ratio. This is, so I had about 15 people at exam review session on Friday. Does that sound about right? Yeah. 15 to 20 maybe, because some people came and left. I'll be doing another one this week, but honestly my office hours this week are going to be very similar. So if you can make my office hours, today it's 3 to 4:30. Tomorrow it's 1 to 2:30. I might add some Thursday if I get requests. So if you would like to meet Thursday and can't meet the other days, please send me an email. I'll see what times work. And then I have another one Friday, 1 to 2:30. That will be the exam review session. But all of them will be opportunities for you to work through problems like this, and we can do some more challenging ones, and then give you some more practice. All right, so we're done, right? Have you guys clicked in your answer? CHO, typically, and then whatever other elements. Yeah, I don't know if it really matters. Does it matter if N or O is last? I don't care. How about that? So for me, that's irrelevant. All right, we have 45 responses. 47. All right, let's see how it shows up. I don't know if the short answer's gonna show up. Josh. All right, so we have 2/3 of the class doing CH5N2O, CH2. All right, where's the other big percentage? So this one and this one. So basically switch the order of the N and the O. And that accounts for the majority of the class. Okay? Is that the molecular formula?
No.
No.
All right, so that is the ratio of carbon, hydrogen, to nitrogen, to oxygen. So which one of these is most likely my favorite jug of choice?
Okay. Okay.
It's okay if you like coconut. It's making you a pretty good
All right, so we heard some strong opinions of what they think the answer is. I want you to look through these options, and I want you to decide if it's one of them, if it can be more than one of them. Go ahead and click in your answer and think through it in your groups. You're welcome to talk to others. Don't comes to that, so the provost or chancellor.
I'm sorry. I go into the last segment just till Jason. I promise.
By the way,
All right, closing out. Why is D or E the correct answer? Mohammed?
Well, because caffeine and dicaffeine have like the same ratio. It's just doubled up, and it's the closest one to what we had as our first problem.
Well, what do you mean closest one?
Well, you have 8 carbons on caffeine and dicaffeine. We had 4 carbons.
Remind me, what is? Tell me the empirical formula again.
It's C4H5, N2, and O.
Okay. So what you're saying is that any molecule with this ratio of elements, it's possible that that was the reactant in the combustion reaction, in the elemental analysis. So is there any way this one, cocaine, can be it?
No.
Why? Say again? All right, so we have an even number of carbons. There's no way that the molecular formula will not have even numbers. So this is not possible. What about ibuprofen? I love me some vitamin I, but I don't take it every day.
Good that it's not.
All right, so we have 2 with even numbers. And then out of those 2 with even numbers, we then look at the ratio 4 to 5 to 2 to 1. 4 to 5 to 2 to 1, 4 to 5 to 2 to 1. Okay, that last compound doesn't exist. I just made it up to prove a point. It'd be like 2 caffeines, diaphene. All right. Wasn't really supposed to be funny, but I mean, it served a point, right?
Oh, that's funny.
So this is another way you can ask the question. So instead of that last question I asked, which one is it? You could ask this question. So make sure, talk to your neighbor. If this was the first question we saw before the last one, how would we answer this question from the information you have? All right. I hear a lot of good discussion. So, can I hear from Joey?
It's false.
Why?
Molecular formula for that is 97 or...
The molecular weight?
Yeah, that's what I'm asking.
So if we add up the mass of 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen, what do you find the mass to be?
97.0965. And so,
Units
grams.
per every mole of that.
So that would be one of those, and it would act, if that was the molecular weight or whatever, then it would be the dicaffeine, whatever, because then it would be 2. No,
I think that's supposed to say empirical formula.
No, it's a true or false statement. Is that the molecular formula or not? We know it's the empirical formula. We found this in the empirical. And I think you might have just flipped it, so let's talk through it to make sure we're all comfortable with this.
Yeah.
So if this weighs 97.096 grams per mole, it can be any multiple of this. So it could be C8, H10, right? It can be C12, H15, or it can be any multiple of that higher and higher. Which means that the molecular weight for the molecule itself can be any multiple of this. So if it was caffeine, that was twice the numbers, right? I think it was C8, H10, N4O2, is that right? Mm-hmm. So what would you expect the molar mass to be in that case? It would be double this, which would be 194.19. So that's one way you could identify and know what the molecular formula is. What about diaphene?
It'll be double that, the 194, assuming it existed.
So the other way I'd like to say it is it's 4 times the empirical formula, right? I think it was 16 carbons and whatever else. So it would be 4 times this molar mass. Questions on how we identify whether the empirical is the same as the molecular? I have some practice problems on the page that I'll pop up here in a second. Any questions so far? I think I have this written out. So that is my drug of choice. You see me every day ingesting this drug. So this would be an example of an exam question that I would ask you on this topic. This is also listed, I think this is written out in on your worksheet for today. So similar to today, giving you the percent of carbon, hydrogen, nitrogen, not telling you how much oxygen, and then you have to identify which of multiple choice options represent that ratio, that percentage. Okay, I did not give you enough space to do it in class because we're not doing it in class. I have this problem worked out, hidden in my slides, so you can go to content on Blackboard, download the slides from today. I would work through the problem on your own first before you look at the slides to see how I did it. And then here's another example of one you could do. This is going to be the more challenging version of that because you have to find how much of each element you have first.
That's like the homework.
Like the homework. Okay? So I highly recommend trying these out, coming to office hours this week or the exam review session, and then we can work through any kinks or any challenges or figure out how to do it a little bit faster if you're able to get through it, but it takes you a while. And then this one I would give you options most likely as well, but you wouldn't just be able to circle one, you wouldn't get any credit for just circling an answer. It's a 25% chance of getting it right. You'd have to show me your work. And so it might be a multiple choice, but it would be in the short answer section because I would look at your work. All right? It's not worth just 3 points for you to solve a problem that's this big.
Okay, so I have a question. Like, if these questions take 3 minutes and we got 50 minutes on an exam, how many questions are you talking about on this?
46 of these. All right. I tried to consider that and be as fair as I can with the number of questions. I mean, that's all I can say. Right? Like, I don't have the exact number yet. No. All right. So let's shift gears a little bit and let's start thinking about solution chemistry. So have you guys heard the term electrolytes? Is that something you've used in lab? All right. So let's get a definition of electrolyte. I have part of it up here, but I want you guys to talk amongst yourselves and come up with a very good definition of when this applies.
I don't know how you use it. I don't even
All right, can I have someone share where this applies? Hand raised. Sarah, thank you. where are electrolytes relevant and what does it mean?
We need electrolytes in our body. I forgot what it does, but
Okay, so they're biologically relevant. It's what plants need. Anybody?
It's just something about whenever you put it in water and it breaks up, the ions have a positive charge, something like that.
Almost. You
That's
got
all I know.
2/3 of the way there. So if they break up and they have a positive charge, what else has to be there? And a negative. Okay, so we've been talking about salts. We've been talking about solubility of salts. One way to kind of help you remember this is, what does electro usually mean? So electricity. And if you have plain tap water, no, not even tap water, if you have distilled water, if you only have H2O, it actually is a really bad conductor of electricity.
Oh, yes, awful.
So what you can do to increase the conductivity of water is to add ions, positive and negatively charged ions. Sodium chloride, right? Put sodium chloride in, it dissolves, now we have a negative and a positive charge, and those can actually help electrons move through the water much better. So a strong electrolyte does that to a large extent. A weak electrolyte does that a little bit. So vinegar, if you put vinegar in water, then you get a little bit of that. About 3% of vinegar separates into an H+ and acetate. But most of it stays together. So an electrolyte is going to be specifically about dissolving in water, like Joey said. We take something, we dissolve it in water, and when it dissolves in water, it separates into its two ions. And you guys worked with this when you did the molecular formula, the ionic and the net ionic. So does anyone more accurately know what it needs to do in order to be a strong electrolyte?
Basically dissociate.
Okay, so it's actually 95 or greater percent of it needs to dissociate to be considered a strong electrolyte.
And it disassociates into its ion.
Correct. And we're going to talk a little bit more about what that looks like because you've had some problems on it already, but we want to be really clear that we're on the same page about what dissociates and what does not. So all this stuff you see up here on the board, this is Henderson-Hasselbalch equation, this is second semester Gen Chem from the previous class. This actually describes that while we say that a reaction happens, and we assume in first semester Gen Chem that it always goes to products, that's not really the case. So a lot of reactions will go forwards and backwards. And so if we have 95% that forms the products, in this case dissolving and separating, that is a strong electrolyte. If it's less than that, then it's not. So we'll be spending some time calculating that in second semester. So this term strong acids is one that I need you guys to grab hold of and to be able to recognize a strong acid. So there's 6 strong acids. They're in table 3.1 in your book. You will be expected, if you ever see a strong acid, to know that it does fully dissociate and release one H+. Have you guys worked with strong acids in lab?
Yes.
What's the strong acid that you guys have worked with in lab? Say again?
hydrochloric acid.
Hydrochloric acid. It's assumed that when hydrochloric acid dissolves in water, that it dissociates into H+ and Cl-. What you're going to see is that if H+ is around water, a lot of times we write it as H3O+. Because that H2O has a lone pair of electrons sitting on it, right? One of the 4 steric domains. And that H+ is going to be more stable being associated with that lone pair. And it ends up making H3O+. The other way to write that you'll see pretty frequently as well, those two are identical. One is you're kind of ignoring that water's there, but you're saying water's everywhere. This is probably the more accurate version up top, where if it's in water, H+ doesn't exist by itself. It's going to be sitting on water and make H3O+, hydronium ion, which is one of the polyatomic ions you guys know. All right, and so if we have 95% or greater dissociation, we're going to draw the full-headed arrow. We're not going to be drawing an arrow that goes back and forth like you see over here. So here's a handful of our strong acids. This is not all of them. I need you guys to go to table 3.1 in your book. Make sure that you will recognize all 6 of those strong acids. One that's a little trickier is this bottom one.
Sulfuric acid.
So when sulfuric acid dissolves in water, the definition of a strong acid is it releases 1 proton. H2SO4, after releasing 1 proton, is HSO4 minus. This is also an acid. This can also release a proton, but this doesn't do it to 95 or greater %, so this is not a strong acid in the products. You can write another equation if we wanted to. So where we have hydrogen sulfate dissolved in water, what's different about that last equation, Trey, than all the others?
Oh, there's
Great, so we have an equilibrium arrow. So the equilibrium arrow shows that while this reaction does happen, that sulfate is not always as stable by itself. So it'll steal that proton back from water, recombine, and give you hydrogen sulfate and leave water by itself. That is not a strong electrolyte at the bottom. It's not a strong acid. But it's related to a strong acid through the first of those 2 equations. All right, we're going to spend half of second semester discussing equilibrium reactions, trying to figure out how far do they go and what conditions change how far that reaction goes.
And you said these were in what table in your book?
3.1. I think it's even written on the worksheet, is that right? Maybe not. And actually, I think I have them listed here. So whenever we see these, we know that they're going to be a strong electrolyte, they're going to release 1 proton, and when they release the proton, are you guys comfortable with the term proton?
Yeah.
What does proton mean?
Hydrogen ion, except when it's deuterium.
You can't shout out the answer for every question. Let people have a chance to think. Okay, so usually when I say a proton, you think about a subatomic particle, right? You think about the nucleus. So why do I keep referring to protons, that these release protons? Talk to your neighbor for a second. Why am I referring to them as releasing a proton? It's not a nuclear reaction. All right, can I hear from Aaron? Fantastic.
I didn't hear any of that.
So, I'll reiterate. The H plus ion, being a hydrogen, how many protons does it have?
1.
Hydrogen is defined as having 1 proton. And if we have a normal hydrogen, it's 1H. The mass number is 1, so how many neutrons does that hydrogen have? 0. Right? Otherwise, this mass number would be greater than 1 because that 1 mass number comes from a proton that defines it as hydrogen. If this was a 2, it would be a proton and a neutron. So most hydrogens only have a proton and 1 electron. But if you think about HCl, that HCl, one of the, I should probably draw all the lone pairs, right? That 1 valence electron, the 1s1 electron from hydrogen, is shared in this bond. So if this bond is dissociated, it leaves these electrons behind with chlorine to become chloride. meaning the hydrogen now has 0 electrons. So what do we have left? If it had a proton and electron, it left the electron behind. We only have a proton left. So a lot of times when you hear chemists, we refer to how many protons are released or what's the concentration of protons. We're not referring to a nuclear reaction, we're referring to H+ ions. That's very common terminology. So when we talk about the pH of solution, pH of the solution is also defined as the concentration of protons in solution on a logarithmic scale. And we'll spend some time second semester with that. All right. In addition, you need to recognize that all of the group 1 and 2 metals attached to hydroxide are considered a strong base. We're going to spend a lot of time second semester with those, but most of the time I think you'll just recognize that that will happen because they're a salt. But these ones maybe are less obvious that they're strong electrolytes because it's a hydrogen attached as opposed to a metal and a non-metal. Quick question?
Yes. Strong base. If you have a group 2, then and hydroxide is, for a group 2 cation and hydroxide, you would have 2 hydroxides each, right? So wouldn't it dissociate into 2 hydroxides?
Correct. But it's not. So our definition of a strong acid is releasing 1 proton. Our definition of a strong base is it releases hydroxides, 1 or more. Which is your point, right?
No, I think my point is that if you have like CaOH minus or plus, sorry, does that then further dissociate into hydroxide?
Yeah, so calcium hydroxide releases 2 hydroxides for every calcium hydroxide. And we're going to get into that.
Okay.
So let's spend some time talking about what that means to dissolve in water. I think this is in the worksheet question 6.
Your question.
What? Couple more seconds. So where are we at on this question? 2-to-1 ratio. How do we answer this question? What are we thinking about? You guys have learned some stuff in this class, hopefully. Mohammed, how do we apply our previous learning to this question? And I did it again. Moab, go ahead.
Cation solution, so cations are positive, so the solution is filled with positive ions, and I know that positives and negatives attract, and oxygen has a negative charge on its own, a negative charge, so they would, the oxygen atoms would bond together with the cation.
So your point is twofold. So one, we need to know the definition of cation. Is it a positive ion in solution? If we don't know that, we can't answer this question. I think I mentioned I always remember that because the T in cat ion looks like a plus. Anion is a negatively charged one. Anion doesn't have anything that looks like a plus. So that helps me remember it. The second thing is, so he mentioned something about negative, positive interactions. So if we look at this molecule here, let's actually answer the next question, then we'll come back to some details about that. So I'm going to close this guy out. So I agree with Mohib's statement that the oxygen atom would be attracted to cation solution. Do you agree with this statement, which is what Mohib just said? You're welcome to check in with your neighbor if you'd like. How are we feeling? My clicker base is not showing me the results today, so I'm going to have to go live. Okay? So most people agree with Mohib. Why are you guys wrong? Talk to your neighbor. Why is Mohib wrong and this statement is false? Try to figure out why that answer is wrong.
My dad's looking right now for sculptures, paintings.
Is it just the wrong reason that it is? Like, is it true, but it's just the wrong reason? Is that one?
Like, where's the right and where's the wrong?
Yeah, that's what I want
here.
to know. 'Cause I'm confused.
Okay.
Yeah, okay, I got that right.
So this is what we're discussing. I agree with Mohib's answer to the first question, but I disagree with his statement of the justification for the second. So can I hear from a new group who talked about this, who might have some insight into why we might have overlooked something? So if Joey was talking about it, then I want to hear from someone in his group, or you have a question about it.
I didn't really talk to anybody. I'm just guessing. There's nobody else on the radar.
Okay, let me see if we can get someone else to raise their hand. If not, we'll come back to you. Eric?
It doesn't have any formal charge on the oxygen atom, but it does have a lone pair sticking out.
Okay, great, we're on the right track. So if you were to go and determine formal charges, what do we have to include first in our drawing of the Lewis structure? How many? Two lone pairs on water. So if we do formal charges, we'll look and we'll see 0 formal charge. Okay, so that means that we can completely discount that. What we might say is, oh, well, it has a... we'll go back to that in a second, actually. Okay, so it has 2 lone pairs. So then why is it that a positively charged cation would be attracted to that and that would help it dissolve in solution?
Is it because oxygen is partially negative?
Very important word to use there. Say it again.
Partially negative.
Partially negative. Why is oxygen partially negative? Yeah?
Does that have something to do with electronegativity?
It does have a lot to do with electronegativity. What does it have to do with electronegativity? Okay, so you guys just learned about molecular shape and about polarity and about dipoles and all this stuff, right? You have to apply it to a new problem when we see it. So this molecule, water, has 2 polar bonds because oxygen is more electronegative than hydrogen. That dipole points towards the oxygen. So that means that those electrons that are shared between hydrogen and oxygen are actually more frequently found towards oxygen. It does not change its formal charge, but it has a little bit more electron density. And so we say it's a little bit delta, a little bit more negative, and the hydrogen's a little bit more positive. And that exists on both of those OH bonds. That's why water is considered to be a polar molecule. If we say it's a negative charge, what would that imply?
But the whole thing was negative. Or it wasn't partially negative?
So if this is a formal negative charge, it would have to take all of these electrons, and that means that this would dissociate into OH minus and H plus, meaning it's an ionic compound. Is that an ionic compound? Okay, so we have to be able to distinguish between an ionic compound and a molecular compound. A molecular compound is one with covalent bonds that very rarely will dissociate. An ionic compound will be one where those bonds very frequently dissociate and form a positive and a negative charge. Josh?
Okay, so why in that question, why are you saying not because it has a formal negative charge rather than, why are you saying negative charge rather than positive charge?
So it has a partial negative charge. That is the key to this question.
But wouldn't a partial negative charge still be negative charge?
So when I see a lot of students answer this question, they say, well, it's negatively charged, implying that it has a -1, which means it's an ionic compound. So that's the distinction. So in your head, you can word it how you want, as long as when I read it, it's very clear to me that you know that that is not an ionic compound. Is that fair? All right. So our water molecules, all of them have 2 polar bonds they have a larger electron density around the oxygen than the hydrogens. So that means that if you go into solution and you have a cation, what do you notice about the cation? What happens to all those water molecules? Are the hydrogens pointing at the cation or the oxygens? So if we look at these two spheres here, we have the equivalent, it's magnetic instead of electrons, but we have a blue and we have a silver, or a blue and a green, sorry, small and a large. Talk to your neighbor and guess which one of these, if this is sodium chloride, which one is sodium and which one is chloride? And then we'll test with the water molecule. So right now all we have to go off of is size. With these two, blue is smaller, green is larger. Which one is sodium ion, which one is a chloride ion?
Which one was larger? Green is larger?
Green is larger. Alright, raise your hand if you think the chloride ion is the larger green one. Raise your hand if you think the smaller blue one is the chloride ion. Why?
Because it's closer to the gas, so it's more dense.
True. So why do people answer the other way around? Why would you answer that chloride would be the green one?
Because on the chart has a bigger atomic radius.
So if we just compare chlorine and sodium, I agree with you guys. Sodium is going to be the larger one. But this is not sodium and chlorine. This is sodium ion and chloride ion. So let's test. Let's take water. If the blue one is chloride, what part of the water molecule is going to be attracted to it? The partially negatively charged oxygen, right? So we have a simulation of something similar here. The larger and smaller ones, this is sodium chloride. In a solution of water, we have a brick of sodium chloride. The larger one is the one with a negative charge. It has more electrons than the neutral element. And about how many water molecules do we need to solvate each of these ions? So when you think about a salt dissolving, I want you thinking about the molecular atomic level of that salt dissolving. I want you thinking about water molecules having a partial negative and a partial positive, and that those can come and be attracted to the negatively charged chloride ions or the positively charged sodium ions. And what we find is that there's about 6 or so water molecules needed to solvate or to dissolve every chloride or sodium ion. And so from that we can kind of back out how much of a negative charge does oxygen have? Is it 0.05? Is it 0.5?
It's about 1/6, or
It's about 1/6. Because if we need 6 of these to mask a positive charge, that means that this is about 1/6 of a negative charge. All right. If you can, try the next question on your own. Look through the questions. We'll finish these on Wednesday in class. If you want any help on the concepts of the homework. Did anyone not finish the homework, by the way? Would it be helpful to give you guys until the end of the day to reopen that?
Yes.
And you could up your score. All right, I'll see if I can send it to the end of the day. And then make sure you're comfortable on those before you take the quiz. Come to office hours, 3 to 4:30 in science lab 273. Which section?